Our next speaker is Yakov Babichenko, who will tell us about populations' feasible posterior beliefs. Yakov,
Thank you. So this is joint work with Itai Arieli, my colleague from the Technion. And let me start with the setting that we consider, just one line, 2 lines. So we have n Bayesian agents who share a common prior about an unknown state, omega, and they are exposed to some information about the unknown state, and they might be exposed to private information that others do not observe. And the question, which distributions over posterior beliefs can the agents have? Okay? Just to be on the same side, let me give you a concrete example what I mean by being exposed to information. So the way to treat information is it's a correlated distribution between states and signals that are observed. In this case, we have a single agent who may have 3 possible signals, and this information structure induces the following distribution of posterior. So after being exposed to S1, the agent will have a posterior of 2/3, and this actually happens with probability 0.3. So in many applications, we do not really care about this information structure, but rather care about what are especially if it's a decision maker, we care only what are his posteriors and which probabilities they are occurred. Okay, so we will be interested in this notion of P, not of I. For the case of a single agent, this question has a very elegant answer. So let me just give one terminology that I will use, the notion of feasibility. So a distribution P is feasible if there exists some information structure that induces this distribution of posteriors. And the answer for the single agent is sometimes called the splitting lemma. It appears already in Aumann and Maschler and in Blackwell. It simply says that if the expectation is the prior, then it is feasible. And this is exactly an if and only if characterization. Okay? This is a very useful lemma. Let's say what happens if you have 2 agents. So first thing that I want you to notice is that the expectation is no longer, it's obviously necessary condition because every agent must have the expectation, but it's no longer sufficient. Here is an example. Assume that the state is, with probability half, agent 0 is sure that the state is 0, and agent 1 is sure that the state is 1, and with probability half, the other way around. Agent 0 is sure that the state is 1, and the second agent, okay, sure that the state is 0. So this distribution has the correct expectations. Yeah, the expectations are 1/2, but obviously it's infeasible. In fact, any distribution that 2 Bayesian agents can never have opposite opinions with positive probability. So what is the characterization for this question? So we saw that the condition is not, does not provide, the expectation does not provide us a characterization. So the characterization for the case of 2 agents and for binary state, it has been introduced by David, De Groot, and et al. So it essentially, you don't have to read this inequality, but essentially it says that some inequality should be satisfied for every pair of subsets A and B. This is type of a duality theorem. And this inequality has very nice interpretations in the context of the agreement theorem and in the context of the no-trade theorem. But on the other hand, it's quite complicated object. It requires search over subsets. What's going on if we try to extend it to, say, to more than 2 agents or to more than binary states? Then the characterization becomes even more complex. So there are characterizations, but those extensions require search over functions. Here we have, in some sense, search over indicators. We just consider all the pair of subsets. There we need to consider all the functions. Okay, so those are, in some sense, on the one hand, very nice characterizations. On the other hand, quite complicated. And here I get to the topic of the talk today. I want to ask exactly the same question, but in an anonymous manner. So, and let me introduce you the question by an example. So let's consider a binary state space. We have a prior, mu, and we have a lot of agents. You can think of many agents, n agents. And the posterior of every agent is either 1/4 or 3/4. Okay, this is why I call it an example. So no matter what information they are exposed to, they essentially will either have a posterior of 1/4 or 3/4. And now every profile of signals induces a frequency of agents who will have the high posterior. So 0 means that everyone has the posterior 1/4, and 1/n means that one agent has a posterior of 3/4 and the other 1/4. So since every signal realization induces a frequency of agents with high posterior, then any information structure induces a distribution over frequencies. Okay, those are distribution over frequencies of agents with high posterior. Let me, why I call it an anonymous variant of the problem, because notice that here I don't care which specific agent holds which posterior. I'm only asking how many agents hold each posterior. And this is the main distinction of the problem that I pose here. It's an anonymous variant of this problem. And we ask the same question: which distribution of posteriors are feasible? And here is the answer. A distribution of posterior is feasible if and only if it's a mean-preserving spread of the distribution that has two atoms, one at 1/4 and one at 3/4. Okay? This is the if and only if characterization. And in fact, it's quite simple. So let me show you the proof. So mean-preserving spread can be written also as we can write this distribution as a sum of two, as a linear combination of two distributions, one with expectation 1/4 and one with expectation 3/4. So the argument for showing that it's necessary is the following. So conditional on state 0, every agent has the posterior 3/4 exactly with probability 1/4. When we look at it from the perspective of an individual, this is something, simple calculation can show you. It just follows from the fact that he is Bayesian. So therefore, conditional on state 0, no matter what are the correlations between these agents, the expected frequency of agents with posterior 3/4 must be 1/4. And this is exactly so P0 in our case will be the distribution, the frequency of agents with high posterior at state 0. Okay, and similarly you can do for conditional on state 1, and we get one direction. For the other direction, we again do maybe the most naive and simple thing that we can imagine to do, maybe the first thing that comes to mind. So at state omega equals 0, we draw a random subset of agents, but over the size of this random subset is drawn according to P0, and we send them the high signal. And at state 1, we do the same, but we draw the size of the subset according to P1. So all that remains to show is that after observing the signal H, an agent holds the posterior 3/4. And the simple calculation show that this is indeed the case. Okay, so now we have kind of simple arguments that show us that succeeded to solve this example. And then the advantage of having simple arguments is that they, in some cases, including this case, can be extended to much more general settings. So what is the object that we consider? So this is the object. So there are too many deltas, so let me explain them. The delta of omega is just a posterior belief. Delta of omega is the distribution of posterior beliefs in the population. And finally, the first delta is the randomness according to the randomness that is caused by the signals. Okay, and the theorem is essentially says that it provides a characterization for the anonymous variant of the feasibility question. It says that the distribution is feasible if and only if it's a mean preserving spread of some weighted atoms. And this p hat omega, those are essentially, they can be easily deduced from the initial distribution p. So let me just point out that so many times when we talk about information, we are used to think of mean preserving spreads or mean preserving contractions in the space of beliefs. Note here the difference that here the mean preserving spread is operated on a different space, the space of frequencies of beliefs, which is slightly different. Okay, so what are the good news about this theorem? So first of all, the complexity, the characterization doesn't increase with the number of agents. In fact, when you look at it, it looks as if it even does not depend on the number of agents. So let's correct it. Right, so the distributions that we are talking about should have, right, so the distribution of frequencies should be either 0 or 1 over n or 2 over n. So the second delta essentially should be delta over n. The characterization does not significantly increase with the number of states. It just adds few more atoms to the mean preserving spread. It's not so complicated, but there is also a shortcoming that you should notice that it does increase with the number of possible posteriors. Why? Because just the notion of mean preserving spreads just the notion of mean preserving spreads becomes a relatively complex object in high dimensions. So let me show you one application that we can do with this theorem. So a question that has been previously studied is the question how polarized, how different the opinions of two Bayesian agents can be. Okay, so and let's focus on this question from the perspective in the binary state case. So here is a possible measure for polarization. Take the two opinions that the agents have and just look at their difference to some power alpha. Okay, this is a possible measure for polarization. So this question maybe seems, at the first look, may look trivial. It turns out not to be not trivial at all. It has been studied by Dubin, Spitman, and others. Let me tell you the bottom line. The bottom line is that for alpha smaller or equal to, the maximal polarization is obtained by a full information, no information policy. Namely, if I reveal to one of the agents the state and for the other I send no information, this creates a situation where one of them always will have the posterior of 1/2 and the other one either 1 or 0. So and this is the maximal polarization that can be obtained. Just to show you that the problem is not very easy, for instance, for the case of alpha greater than 2, we do not know what is the optimal, what is the maximal polarization. And nothing was known for the case of more than 2 agents or more than 2 states. Let me consider now the case of more than 2 actions. So here is a possible measure of polarization. We look at what is the distribution of beliefs in the population, and we look at the variance of this distribution. Okay? Notice that it precisely corresponds to the case of alpha equals 2 in the case of 2 agents. Because it becomes exactly up to a factor of 1/4, it's exactly the same measure. So it in some sense a generalization of the case of alpha equals 2 for more than 2 agents, for more than 2 agents. And here is the proposition. For every even number of agents, the maximal polarization is obtained by full information to half of the agents and no information to the other half. Okay? I will not have time, and this proposition also extends naturally to, it remains correct, and it extends naturally to the case of non-binary states. So let me just give you a very high-level idea of how we utilize the characterization that I just told you. So we know that P is a mean-preserving spread of some two distributions. Essentially what the proof does, it considers another distribution of frequencies of posteriors that instead of spreading the frequencies, it deterministically puts these posteriors for sure. So there are some issues. But essentially what it does is we can show that this always reduces the variance, and some calculations, after some simple calculations we end. This, by the way, I think also provide an alternative proof for the case of n equals 2. So let me conclude with the sum. Even this simple question we don't know the answer for odd number of agents. We know that full information, no information is not the optimal thing to do. Here is something that beats the full information, no information, but we don't know what is optimal. And in the paper, you can find also other applications in private Bayesian persuasion and in the context of feasible product distribution of posteriors. Thank you.
Thank you, Yakov. We have time for questions. Any questions from online audience? I have a question. So it's kind of surprising that this anonymization simplifies the problem of feasibility. But is there a chance that you can reduce the general feasibility problem as a problem consisting of two parts? First, you decide on the feasibility of anonymized distribution, and then you decide on feasibility given this particular anonymization. And maybe this decomposition gives a simple characterization of feasibility in general. Can it be possible?
So let me a link between the two questions, right? The standard question of feasibility and the anonymous one that we study is that if you want to think of it's another way to say that we try to characterize which exchangeable distribution in the standard space are feasible. And the exchangeable distributions is quite restricting subset, right, of what's going on. The notion of exchangeability is if and only if. It's exactly what we study, essentially. And the subset of exchangeable distributions is a restricting one. Yeah, but.
Yeah, I see. Other questions? Okay, then we will move on to our next speaker.